Hi, AP Statistics. Today we're going to talk about the first page of Chapter 2, Notes. The goal of Chapter 2 is to find out how a particular value compares to the rest of the data. There's a couple sections we're going to talk about. The first one is density curves. So from Chapter 1, we have a clear strategy for exploring data from a single quantitative variable. So again, quantitative, we're talking about numeric data. You always plot the data, make a graph, usually a histogram or stem plot. And actually I'm going to add on, you can also use a box plot here. It is also pretty helpful. So one of those three graphs. You always want to look for the overall pattern. The shape, center spread, any outliers, and then calculate a numerical summary. So numerical summary can be the center and the spread. So whether you're talking about the median and like the 5-number summary, or you can talk about the mean and the standard deviation. So mine are a little bit out of order, just how I uploaded this in here, sorry. What we're adding to this chapter is sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. Okay, the histogram that's up here, yours is to the right in your notes, is symmetric. Both tails fall off smoothly from a single peak. There's no large gaps or obvious outliers. The smooth curve through the tops of the histogram bars is a good description of the overall pattern of the data. So you can see that nice smooth curve would be a good description of this data. A couple notes about a density curve. It's always on or above the horizontal axis. It also has an area of exactly 1 under the curve. Okay, so symmetric and bell-shaped we've talked about. Oh, my graph looks horrible. Okay, let's erase that. Okay. Drawing with this little stylus is a little bit difficult. Okay, so symmetric and bell-shaped sort of is like that. Okay, where your mean, oh, that's off. The mean and the median are very close together and in the center. Okay, right skewed has the right tail. So it's going to curve off like that. The median, again, is the midpoint, so it stays in the center. The mean is going to be higher because it's affected by those large values. And then left skewed, it has, oh gosh, that's horrible. I'll erase that. That's not much better, but anyways, it has the left tail. Ooh, straight line. The median stays in the center. The mean is going to be to the left of the median. Sorry, hopefully yours look better than mine. Okay, the median of a density curve is the equal areas point. So notice we switched to talking about area. The equal areas point, the point where half the area under the curve is to the left and the other half of the area is to the right. Okay. The mean of the density curve is called the balance point. The point at where the curve would balance if it was made of solid material. The mean of the density curve is denoted by mu. Okay, so that's the population mean, and the standard deviation of a density curve is denoted by the lowercase sigma, which is like a circle. Ooh, sorry, not like that. It's like a circle with a line on top, basically. The Greek symbol, it's a lowercase sigma. The capital sigma is like the summation sign, but this is the lowercase sigma. Okay, so mu, mu is how you say that. So I'll just write that over here. Mu, how you say it is mu, and then this is sigma. Okay, both Greek letters, and that's how you say them. Okay, so our first example, we're going to use this broken line density curve. Find the proportion of observations in the given interval. So we want to use the fact that the density curve, what do we know the area under the curve is? Just went over that up here. The area under the curve is always 1, so we're going to use that. And we just have these intervals that we're going to look at. So from 0.6, if I could draw a straight line, to 0.8. Okay, and we just want to find, we're talking about area now. So the area of this rectangle. So all we do, area of a rectangle is, base times height. So here we have our base is 0.2, 0.6 to 0.8, and then the height on the graph is 1. So we get that area under the curve is 0.2. The next one is 0 to 0.1. Okay. And so for this, you can remember these geometric formulas. Otherwise, you can just break it up into shapes that we really know. So if I cut this off, that was supposed to be at 2. I can make it a triangle and a rectangle. Those are areas, the formulas of areas that I know right off the top of my head. So the first one, if we look at the triangle, 1/2 base times height. So my base is 0.1, going from 0 to 0.1. The height is from 2 to 3, so that's an area of 1. Okay, and then I'm going to add that to the area of this rectangle. So the rectangle below it has a base of 0.1 and a height of 2. So for this, you just want to grab your calculator and calculate that. Okay, so when you get those together, you end up with 0.25. Okay, I'm going to erase these marks on here so we can do the next one. So 0 to 0.3, there is a couple ways that you can solve this one. Okay. Again, you can break this up into, like I would break this up into one big triangle and a rectangle, and you can add those together. Okay, which is perfectly fine. So let's go ahead and do that. So the rectangle on the bottom has a base of 0.3 and a height of 1. And then the large triangle, we would do 1/2 base. So the base goes to right here is 0.2 with a height of 2. Okay, so you add those together and you get 0.5. Another way that you could have done that one, especially if there's a lot of different shapes that you'd have to break up and you don't want to do that, use the fact that the density curve adds to 1. And so you could instead subtract this other rectangle, because the rectangle is easy to find. Subtract that from 1 and you get the rest of the area. So that's another way you could do this. Okay. Verify that the graph is a density curve. That just means that our total area is 1. Okay, so since we just figured out I'm going to write from 0, what we just solved in part C, 0 to 0.3, that area equaled 0.5, and then we could do from 0.3 to 0.8, that has a base of 0.5, a height of 1, so it equals 0.5. So when you add these two together, that's the whole area of the curve. It equals 1. So therefore, it's a density curve. Okay, but the fact that the area adds to 1 is what you would use to do that. Thanks.